All right, guys, ready? So this is where we ended yesterday. And we were analyzing this data. And this is the most fascinating thing, is when wash my board. That seems like a good thing. It is not. So here's what we ended up with. We ended up with this graph that was curvier than linear, but not quite as curvy as a quadratic, right? That's a super weird thing. And again, Kepler figured this stuff out in the late 1600s, so I don't know what your problem is, but you know. So he got t is equal to some coefficient times a to the 1.5. Now that's a weird thing, okay? Now in this case, a again is the semi-major axis. If these were circular orbits, we could just use radius. And this is true for all things that are going in a circle too. You just replace orbit. So we decided that this was just as easy to say this is 3 over 2, square both sides, t squared is equal to some coefficient times a cubed. Here's the thing, and this is like the moment, right? Is when you look at this, what this is saying is that for all planets, and in fact, we're going to see it's not just for all planets, it's for everything in orbit around a central body. So in this case, it's the sun. The t squared over a cubed is a constant. The t squared over a cubed is a constant. This is the craziest result. This is Kepler's third law. Just like Newton, this is so funny. So Newton has 3 laws, right? Newton's first law says that an object in motion will tend to stay in motion as long as the forces are balanced. That's Newton's first law, right? An object in motion will tend to stay in motion as long as forces are balanced. That's Newton's first law. But Newton's second law says that the acceleration is dependent on the net force and the mass. But inherent in the second law is that if the net force is 0, the acceleration is 0, which actually is what the first law says. And then Newton's third law is Newton's third law of force pairs. The deal is that there are only two Newton's laws. There's law 1 and 2, which says the same thing, and then there's law 3. But at the time, the church was like a big deal still, and the Holy Trinity of the Catholic Church was like a big deal. And so he decided to write 3 laws so that the number 3 was in the 3 laws, and so that people in the church establishment wouldn't be so upset about the science. 100% true. Kepler does the exact same thing. Kepler's first law states that as objects go around the sun, they speed up when they're closer, they slow down when they're farther, and it's a mathematical ellipse. Every orbit is an ellipse. His second law says if you look at that ellipse, a line drawn from the sun to any planet will trace out equal areas in equal times. Well, if that's true, then the orbits are ellipses, and they have to be going faster when they're closer and slower when they're farther away, which is what the first law says. So he did the exact same thing. He took one idea and he broke it up into 2 laws, and then he has a third law that's different, just like Newton did, because he needed to match the church establishment with the number 3. I find that really fascinating, but this is so cool. This means that for any planet, if you knew the t squared and the t squared over a cubed is a constant, and it's the same constant for all planets, and it's the coefficient of this bad boy right here. Okay? I analyzed it yesterday, which I think is cool. What's that? you want the typo here?
No. At least not in the picture.
Are you sure I don't have a typo here?
Which one did you get on?
I don't know, but this number should be closer to something else. 0.39, 0.71, 1.52, 5.2, 19.95, 19.8, 31.6. 0.24, 0.6161, 1.88, 12. 29.4, 84, and 164.9. All right, well, it is what it is. Okay, so what is our coefficient then? According to this, our coefficient is 0.93. Now, to be honest with you, given the data table, the coefficient should be very close to 1. And we know that because t squared over r cubed or a cubed should be a constant. And if that means that the t squared over a cubed is equal for all planets. So therefore, if I use Earth, it should be 1 squared divided by 1 squared, which should be equal to 1. And we got 0.93. So given some measurement error, we can see that that's actually pretty close. Is that cool? So here's what you need to be able to do. Are you ready? I happen to know that the planet Ceres is in the asteroid belt. Okay? Ceres is in the asteroid belt, and it is about about 2.5 times as far away from the sun as the Earth is. You need to be able to calculate how much time it's going to take to go around. You with me on that? You need to calculate the period in years. All right? Check with your neighbor now, see if that makes any sense to you and your neighbor, and we will go from there.
Good, how are you? Do you know what equation it is?
Yeah, just d squared a cubed, right? This is the constant, is that actually what we want, or?
No, I guess you would just say t squared over 2.4 cubed equals 1.
Yeah.
Anybody get an answer? Anybody?
3.95.
How much?
3.95.
3.95? All right, that's at answer. Anybody agree with that or disagree with that?
Yeah, I got that.
You got that too? 3.95? Are you sure? Are you wearing an Oxford veteran shirt? That is amazing. That is amazing. When my children do something, like they're always working on a goal in their Ninja Warrior classes, and if they achieve their goal, I take them to Oxford to get slushes. Yeah. Brooklyn climbed the rope last night, 20 feet, just all the way up to the top. What the heck? Wrong. All right, so here we go. Ready? So what I'm going to do is, because I know this is the same for all planets, okay? Because I know this is the same for all planets, I can actually use that idea to solve. So I'm going to say that the t squared for Earth over the a cubed for Earth has to be equal to the t squared for series divided by a cubed for series. Do you see how that sentence makes sense? Do you see how that expression makes sense there? Because if t squared over a cubed is a constant, then regardless of what planet or body you put in there, they should be equal. Is that cool? So now I'm going to do a little bit of manipulation here because I think it's a little bit easier to see it this way. So I have t squared for Earth over a cubed for Earth is equal to t squared for series over what? So I know that Earth is 1 AU, so what is the A for series then? It's 2.5 A Earths cubed. That's a E and C were bad choice. That's an E. Is that cool? And so now though you have a weird expression. Okay, now you have a weird expression because I have t squared for Earth over a cubed for Earth is equal to t squared for series divided by, well, what is 2.5 cubed? Ugh. What is 2.5 cubed? Can someone tell me out loud, please? Yes?
15.65.
Louder.
15.625.
Thank you. So 15.625 times a Earth cubed. And now, what we're going to notice is I have a Earth cubed on this side and a Earth cubed on this side. So those can magically disappear, which I like. I'm going to multiply both sides by 15.625. So I have 15.625. And I'm trying to find the period for series, right? So I'm going to square root both sides. What's 15.625? What's the square root of that? 3.9? And I know in this case that the T for Earth is 1 year, so I can plug in 1. And that means that for this planet, Ceres, that exists at a distance of 2.5 AUs, it's going to take 3.95 years to go around. Yes?
Why if you're solving in years though, why don't you just, instead of going through all that, why don't you just do t squared equals a cubed?
So you said just skip all this, just set this equal to 1 and plug in here. You could also have done that. This is a more general, because what if you're not solving in years? What if you're solving in days? Right?
You just convert it afterwards, or you would want?
You can. It just, and sometimes they don't even give to this. They two planets orbiting the same sun. If two planets are orbiting the same sun and one is 4 times as far away from the other, how much more time does it take to go around? So we have a general procedure here that I think makes it's more complicated for this, but makes later problems less complicated. Okay, we're going to try another one. So this is for all planets. Oh, so this is for all planets. What I think is interesting is I'm going to plug into here. Is if I plug in this extra data point here, should it fit good? It's 2.5 and was it 3.95? So it's right here, 2.95, 2.5 and 3.95. It's right there. Does it fit well on our line? Of course it does, because anything orbiting the sun would fit on this line. How cool is that? And that doesn't even mean that it has to be a planet. For all comets, This axis is the semi-major, this axis is the semi-major axis, and this is the time to go around. So they're always talking about this thing that they call planet X, or planet 9. There's some data to suggest that there's a very large planet that exists outside of Neptune's orbit, maybe somewhere in the Kuiper Belt. And they have a sense of how massive it is. And if they knew how far away it is, they would know how much time it took to go around, right? That's the cool thing about it, is you always know, if you know how far something is away, you know how long it takes to go around. You just don't know where it is at any given moment. So it's hard to look for something. You're like, well, because all the planets orbit on the same plane, you know where to look in the sky. You just don't know, like where to look in terms of like up and down. You just don't know where to look in terms of left and right. But if you know how far away it is, you know how long it takes to go around. Let's do a different one. Okay, let's do a different one. Let's talk about Earth. Do things go around the Earth? They do, right? The thing about it is that the t squared over a cubed, all right, so I want to write this down. So a equals r if circular. So you have a circular orbit, A is equal to r. So t squared over a cubed would be constant for anything orbiting Earth. Is that cool? Which is nice. So if you knew, for example, something that orbited Earth, like, I don't know, the moon, if you knew how long it would take the moon to go around, maybe you could figure out how far away it is. Does that make sense? If you knew the constant, which is cool. Which is cool. Now, here's the thing that I need you to know. And this is very important. And you're going to run up against this, but I'm going to tell you right now anyway. This constant here is for the sun. This constant here is for things orbiting the Earth. These two, they are not equal to each other. The constant depends on the central body that the things are orbiting. Okay? The constant depends upon the central body that the things are orbiting. So the t squared over r cubed is the same for everything orbiting the sun, but it's different than the t squared over r cubed for anything orbiting the Earth. This is one of the things when Galileo looked up and he saw the moons, the 4 big moons of Jupiter, that you can see with even a small telescope. He said, oh, that is really cool. And Kepler's like, you know what, I bet the t squared over r cubed ratio is the same for all those. And of course, it is. All those 4 moons have the same t squared over r cubed ratio, which is so interesting. Is that all right? All right, so here's what we're going to do. I want to calculate this constant. Okay? I want you to calculate it. Here's what you're going to start with. We're going to pretend for a moment that well, it doesn't even matter. We're going to pretend that things are going in a circle. We know the centripetal force. Pretend for a moment that the planets are going in a circle. The centripetal force should be equal to the gravitational force, correct? You with me on that? Start with this. Start with the mathematical equations that come to it. You should end up with, somehow you should end up with t squared over, in this case it's going to be t squared over r cubed. All right? Work with the neighbor. See if you guys can't come up with what is the value for the constant for the sun. All right? Start with that. Follow along through. There's going to be a couple steps to get over, but I'm confident you can do it. All right? Do that right now. third job. Very nice. Keep going. Don't forget that if you're going in a circle, right? Don't forget that if you're in circular orbit, the speed is equal to 2 pi r over the period, remember? Right? Don't forget that. You're probably going to need that piece of information. That's pi squared. Don't forget the square root of pi. Because when you square 2 pi, right, the 2 is squared and the pi is squared. Keep going. Ooh, you're getting close. You're real close. Okay.